Welcome to this higher physics video. This is looking at evidence for the Big Bang and stellar temperatures. This is the last part of the R dynamics universe, having looked at the expanding universe section. So what are we going to look at? We're going to look at stars emitting a range of radiation of different wavelengths, and that each star has a peak wavelength of emission. A little bit about the peak wavelength and the relationship with the temperature, and how we can measure the temperatures of stars, and what happens to the temperature of the universe as it expands, and how we can determine explain the present temperature of the universe from this evidence, and how that is evidence for the Big Bang theory, and we'll explain some other pieces of evidence that validate the theory of the Big Bang. So the Big Bang theory suggests that the universe began with a single burst of energy. In the beginning it was small and very hot, and the universe expanded and cooled, and the energy condensed into matter, which gradually formed atoms and then more and more complex structures. It didn't take too long for the first hydrogen and helium nuclei to form from the protons and neutrons, but it took several thousand years for electrons to bind to them to form neutral atoms. So the Big Bang theory predicts that the universe should now have a very cool temperature. And if we can measure this temperature, we can see if this correlates with what we would expect from the Big Bang theory. So we need to understand a little bit first about stellar temperatures, the temperatures of stars, to be able to determine the average temperature of the universe. So if we look at a picture of the night sky, what do we see? Well, what we can see there is there are a range of stars or galaxies, and they are all different colors. Okay, now you might say this is taken with a telescope. Yes, so it allows you to see the different colors, but you can with a reasonable pair of binoculars or a reasonable low magnification see some different stars that are different temperatures and different colors as a result of that. So we've got blue ones, we've got red ones, we've got yellowy white ones. Okay, so the color of the star tells us information about its surface temperature in the same way that a color of a piece of metal or steel that's put into a hot furnace tells us about its temperature. So as we heat up a piece of steel, it firstly goes red, and then it goes a sort of cherry color, and then it goes orange, then it goes yellow, and then it goes white hot as we change temperatures. And stars are the same. These stars of different temperatures have different colors. So an orange star like the Sun is cooler than a blue star like Bellatrix, which is within the constellation of Orion. And the color that we can split into our line spectrum, and so we can see what it actually happens to look like. So there's the picture of Orion, there's the actual star image of Orion. They're not quite in the same orientation, it's a little bit twisted around, and there's the star Bellatrix. And we've also got the star of Betelgeuse, which is the second brightest star in Orion. So we've got Betelgeuse, a red star, we've got Bellatrix, a blue star, we've got the Sun, our yellow star, and what we can see is that we've got a different peak wavelength depending on where we're looking at. So we've got a peak for our red star towards the right, for our yellow star somewhere in the middle, and a peak wavelength towards the left, the much smaller wavelengths, the higher frequencies for the blue stars there. Remember, that's just the visible spectrum that we're seeing there, so it may be that the peak wavelength is actually in the infrared, as we can see from Betelgeuse, or in the ultraviolet section, as we can see from Bellatrix. The stars emit their radiation of a wide range length. We get this graph, and this can be called a thermal emission peak graph. So we've got different temperatures there. So we've got a number of different curves here, and as the temperature increases, the peak is moving slightly towards the left. It's harder to see the peak on the lower temperature ones because of the scale that we've got, and the spectrum is more spread out as well. Okay, but it's a general bit of information that you should be aware of, as the temperature of the star increases, the peak wavelength decreases. Which is what we've got here. So the shorter blue wavelengths are the hotter stars than the cooler, longer red wavelengths. There can be lots of graphs that are like this with slightly different quantities, whether it's irradiance, brightness, intensity, power, but they all have very similar shapes. So here we've got two different stars, Algol, a UV source that has a peak wavelength in the UV spectrum, and we've got Proxima Centauri, which is an infrared source. Okay, there is a relationship between the power emitted in each wavelength is proportional to the temperature. This isn't a relationship that is used in the exam. It is possible that it could be given to you as an unfamiliar situation where you work out the power of the star given the temperature. Okay, sigma there is a particular constant, the Stefan-Boltzmann constant. But again, it would have to give you the information about that to be able to allow for you to determine it. So what we've seen from this star section is that they emit radiation across the complete electromagnetic spectrum. Each star has a peak wavelength that depends on its temperature, and as the temperature of the star increases, there's more energy at each wavelength, and the peak wavelength shifts to smaller wavelengths. So let's move on and look at some of the evidence of the Big Bang. So the Big Bang theory was suggested in 1948 that it should be the single biggest emission of energy in the universe, and there should be a peak wavelength that is associated with this emission that occurred at the Big Bang. Since the universe has cooled quite a lot since the Big Bang, it's predicted that the current temperature of this wavelength would be at 2.7 Kelvin, so there'd be a peak wavelength in the microwave region. So, and because it was all caused by the Big Bang, we should be able to detect the microwave radiation all around us in every piece of direction, indicating that it came from one particular point when the Big Bang took place. So this radiation is called the cosmic microwave background radiation, CMBR, and we can observe this, and we've made a study to detect it and to measure it, and we found it was all over the place. So this is measuring the microwave radiation in lots of different positions, and looking at it, you can see there is some variation within this, but there's not too much. So this is showing it's everywhere, and therefore because it's everywhere, it's evidence of the Big Bang. So our cosmic microwave background radiation is one of the pieces of evidence that show that the Big Bang took place. Okay, you can see there's a peak, and there's lots of points on the graph in terms of our predictions, and the line is mapping exactly what we actually found there. So we get this peak wavelength at 0.2 centimeters. So the cosmic microwave background radiation was shown to be the exact signature that would be left over from a single event that cooled over the lifetime of the universe. the Big Bang did happen, then there would be a big emission of energy. There should be a measurable peak wavelength in the microwave region at a particular temperature, and we found radiation exactly as predicted. Okay, there are some very good videos that explain Olber's paradox, of which I'll put a link in, but I'll go on to talk about it a little bit on the next slides too. So if the universe was fixed and infinitely old, then the night sky should be bright. But it's still dark at night, and that could be because light from distant stars hasn't reached us yet. And the process of the expanding universe means that the wavelength of visible light is redshifted into shorter wavelengths that we can't see. So rather than it still being bright at night, it's actually darker at night because we can't see that electromagnetic radiation that is in the infrared and shorter wavelengths. Okay, so we have three pieces of evidence for the Big Bang and an expanding universe. We have redshift of galaxies and Hubble's law, with more distant galaxies moving away faster than nearer ones, and we can see that is the same in all different directions. We have the cosmic microwave background radiation, cooled radiation from the Big Bang, and that can be seen in every direction. And we have Olber's paradox, why it's still dark at night, because some of the light hasn't reached us yet, because the universe is expanding away from us and it's yet to arrive here, and because the universe is expanded, the light has been redshifted and therefore is not in the form of visible light and therefore is dark. So we've spent the first part of the video looking at stars emitting radiation over different temperatures, with each one having a peak wavelength. There was a relationship between peak wavelength and temperature, although that isn't within the course, so don't expect calculations on that unless you're given the relationship and all the details that you need. We've seen that temperatures of stars can be measured, and then as the universe expands, the temperature of the universe decreases, and so we can estimate the present temperature of the universe, we can measure it, and we can see if that is consistent with the Big Bang Theory approach. And we have our three bits of evidence for the Big Bang Theory: our redshift showing our expanding universe, and our Olber's paradox, and our cosmic microwave background radiation.